Welcome. In this video, I'm going to give you a first taste of engineering design optimization. And specifically, we're going to learn about how mathematical optimization can be applied to the design of physical engineering systems. In this lecture, we're going to go through a definition of engineering design optimization. We're going to talk just in general about engineering design methods, so not just design optimization, but other strategies as well. We're going to discuss the potential value of engineering design optimization as a design decision support tool. And for some context, throughout this discussion, we're going to be thinking about engineering design problems that involve at least some element of physical system design. There are other types of engineering design problems that are, say, purely information-based, but when we bring in physical elements of a design problem, it brings its own unique challenges, and that's what we're going to be focusing on in this lecture and in the rest of the course. So here's the first question. What is engineering design optimization? We're going to look at each individual term and then revisit this question. So what is design? What is engineering? What is optimization? First, what is design? It comes from the Latin root designare, which means to mark out, devise, choose, designate, or appoint. And this word design can be used either as a noun or a verb. When it's used as a noun, it can refer to a plan or drawing or some kind of specification that describes how some element, some object that we are designing is going to be made. When it's used as a verb, it is the act of deciding how something is going to be made. So what distinguishes engineering design from other types of design? To answer this, first let's go through a basic definition of what engineering is. Here's one from Wikipedia. Engineering is the discipline, art, and profession of acquiring and applying scientific, mathematical, economic, social, and practical knowledge to design and build structures, machines, devices, systems, materials, and processes that safely realize solutions to the needs of society. There are a lot of things to point out here and draw your attention to. It definitely requires mathematics, scientific knowledge, but things that go beyond these technical areas, including economics, knowledge of economic markets, social sciences, psychology, practical technical knowledge, and all of this is combined to realize technical solutions that realize the needs of society. Engineered components and systems require some kind of technical knowledge and skills to do things like analyze these systems, test these systems, and of course to design these systems. An effective understanding of engineered systems requires training in relevant mathematics and scientific topics. This requires deeper knowledge of the media of engineering and engineering approaches than what is required of technicians. Technicians have very important practical knowledge of different aspects of systems, but they may not necessarily know the science behind the media of engineering. For example, the materials used in engineering, or the chemistry, or other technical aspects of engineering systems. Success in engineering also requires linking technical capabilities to the goal of meeting actual societal needs. It needs to go beyond intellectual curiosity or passion for a particular interesting technical topic. We need to have knowledge of economics, of markets, of social and human elements. Engineering knowledge and capabilities expand the complexity of what is possible for humans to create. Let's move on to the next term. What is optimization? Often this term, optimization, is used colloquially among engineers to mean things like improvement. For example, using some kind of expert intuition or knowledge to do some manual tuning to improve efficiency or other aspects of performance. Or, for example, in the past, I worked at a software company, and it was very common to talk about code optimization. And this often referred to getting the code to run more efficiently, reducing the execution time of the code. If we're talking instead about formal mathematical optimization, it means something different. We need to distinguish the precise mathematical definition of optimization from the informal use of optimization. Here is a high level of describing mathematical optimization. Given some function f of x, find the value of x that minimizes f of x, the function f of x. Now, we can talk about either minimization or maximization in optimization, but it is fairly standard to talk only about minimization. We can convert a minimization or a maximization problem to a minimization problem by simply changing f of x to minus f of x. And we'll talk more about other transformations like that in problem formulation. But most of the standard algorithms that are available to you are designed around minimizing a function. So if in mathematical optimization we're given some function f of a variable x, and we want to find the value of the variable x that minimizes f of x, we can visualize it this way. Here's a sketch out of a textbook, Principles of Optimal Design by Papalambros and Wild. And here we see a continuous function f of a single variable x, and we can see how the value of f varies with the function x. And we're interested in finding the lowest point on this function. And the ability to find the lowest point on this function, we're going to see later in this class, it translates to the ability to make better design decisions. So if we're just thinking about the mathematics of this, though, we want to understand how do we identify very efficiently what is the minimum of this function. So here, x in general, the independent variable, or sometimes we call this optimization variable. This can be either discrete or continuous. A discrete variable, it can take only on a finite set of values, whereas a continuous variable can take on an infinite number of values. And say between point x2 and x3, for example, here, if we have a real continuous variable x, then we will have an infinite number of values that it can take on between points 2 and 3, and there are no holes or gaps in the number line. It's just a completely continuous variable. We can have in optimization problems either functions of a single variable x, as we see here in this visualization, or a multivariate problem where we have a function that is dependent upon more than one variable. And in that case, it's standard to represent the set of design variables or optimization variables as a vector x. And in the notation that I use a boldface symbol to represent a vector, and then typically this non-boldface font to represent a scalar. These problems can be unconstrained or constrained, and there are different types of constraints that can be applied. And we're going to see that in design optimization, constraints will be very important to formulating problems and the resulting solutions. In this case, we're looking at this univariate function, and these shaded areas to the left of x1 and to the right of x7, those represent infeasible areas, regions, and these correspond to bound constraints. So here in this problem, we are trying to find the minimum of the minimum of f, which is a function of x, but stay within the region between x1 and x7. So we have a set of bound constraints between x1 and x7. That's an example of a constrained problem. We'd like to find where the minimum is, and these minima, they can be local, global, boundary, or interior optima. What do I mean by these different definitions? If we're talking about a continuous optimization problem, a local optimum is one here, like at point x2, where if we're at point 2 and we move in any direction that's available to us, there's no decrease. The function only increases. So if we move locally, this is a minimum. Any local movement is going to result in an increase in the function value. We have here at point 3 a maximum. Point 4 we're going to learn more about later, called it is a stationary point. It's also a saddle point, but it's not a minimum or a maximum, but it is an important type of point. And then point 5 here, this is both a local minimum and the global minimum. At least looking across this entire feasible domain between x1 and x7, at x5 we have the global minimal value of the function x. 6 here we have a local maximum, and then at 7 here we have a boundary local minimum. So if we have a boundary minimum, then that usually implies that we are right up against the edge of one of the constraints, whereas an interior optimum, such as points 2 and 5, we're not right up against any of the constraints. Point 1, this is a boundary maximum, so it is a boundary optimum. Mathematical optimization really is a very broad topic, and in this class we're going to focus on a specific subset of optimization problems. It's not going to be a really comprehensive treatment of the broad class of mathematical optimization. We're going to focus on problems that use continuous, smooth, objective functions. And when I say objective function, I mean the function that we are trying to minimize or maximize. We are treating problems that involve continuous, real optimization variables. And in general, we're interested in problems that have more than one optimization variable, or multivariate problems. We are looking at problems that, in addition to having continuous smooth objective functions, we have continuous smooth constraints. This will make a little bit more sense later on what I mean by continuous smooth constraints. We can define constraints in general using constraint functions, and these constraint functions themselves need to be continuous and smooth for the class of optimization problems and solution algorithms we're going to learn about to work. Objective and constraint functions in general may be nonlinear, as opposed to just a linear function that would look like a straight line if we are looking at a plot of it. And if we combine all of these things together, it forms what we call a nonlinear program. This is what we will refer to as a standard nonlinear programming formulation. Here we're trying to minimize the objective function f of x with respect to the optimization vector x. So we're trying to find the value, the multivariate value of x that gives us a minimal value of the objective function while satisfying these constraints. So these are the constraint functions. G of x corresponds to inequality constraint functions. H of x corresponds to equality constraint functions. Something to point out here is that G and H, using my notation, these are bold. These functions are vector-valued functions in general. And so G and H, the outputs of these functions, have more than one output. So here in this compact representation, we can define a nonlinear continuous optimization problem using these two sets of constraints. And you might be wondering about this term, nonlinear programming. So nonlinear obviously refers to the type or class of functions that we're using in these optimization problems. But programming is more of a historical term. Some of the original uses of optimization were used in more operations research problems like scheduling problems, planning, or in the military operations, creating optimal programs for different things. And so just when you hear the term nonlinear programming, just think about problems that are defined in this way, where we're trying to optimize some objective function, and we have some sort of general continuous constraints, and we have a continuous set of optimization variables. We can visualize what a nonlinear programming or continuous optimization problem looks like by thinking about trying to find the minimum of a surface. So earlier we were looking at finding the minimum value of a curve, but if we have something that's a function of more than one variable, then it's not just a curve, but it's a function of many different variables. So if we're thinking about something that's a function of two variables, then it looks like this surface in 3 dimensions. So for example, if we are walking around in this area and we have different values for latitude and longitude, then that's going to put us at a different elevation depending on our location. So this is Meteor Crater, Arizona. Here's a topographic map of this. So from calculus courses, you've probably encountered level sets. A topographic map is basically the level sets where each of these curves corresponds to an isoline, or a line where the vertical elevation is equal all the way around this line. So we want to find the north, south, and east-west directions, or the latitude and longitude values that are going to put us right at the bottom, the minimal elevation of this crater. So this is one nice way of thinking about mathematical optimization. It's similar to finding the bottom of a surface. And in engineering design optimization, we're usually looking at problems where we have more than one optimization variable. And so this sort of visualization helps us to conceptualize what's going on. So here the optimization variable would be this vector x, x1 and x2, that corresponds to latitude and longitude. And the objective function here would be some function of the position, the two-dimensional position, that gives us the elevation, the vertical distance above sea level. What we just saw corresponded to an unconstrained optimization problem. What happens when we bring in constraints? We looked at the univariate problem a few slides ago where we had bound constraints, but constraints can be more complicated than that. If we have nonlinear constraints, they can look something like a fence. If we have an inequality constraint, a nonlinear inequality constraint, then this conceptually translates to trying to find the bottom of a valley, but you have to stay on one side of a fence or the other. So that's just conceptually what the inequality constraint translates to. Whereas if we have an equality constraint, a nonlinear equality constraint, then that's sort of like requiring that we have to stay on the fence and trying to find the minimum elevation along the fence. And we're going to learn about different methods for actually trying to find these locations, these boundary minima, in a very efficient way. And these methods, primarily that we're going to learn about in class, are based on the mathematical definitions of optimality, either for unconstrained problems or constrained problems. Here's another example of a challenge problem that I've created a little while ago. This shows the level sets of an unconstrained optimization problem, and it might be a little hard to gauge what's going on here at first, but this is a very complicated surface. and it has thousands of local minima. And it's a big challenge to find which local minimum in this space is actually the global minimum. And this square right here in the middle, this shows approximately where the global minimum is. So this may give you a little sense of the complexity and the difficulty of some potential nonlinear programming problems and the kinds of algorithms that might be needed to solve these problems. Many other optimization problems exist besides continuous optimization nonlinear programs. For example, we can have different kinds of discrete variables. We can have integer discrete variables, or we can have categorical discrete variables. The functions could also be discontinuous, for example. We could have non-smooth problems where instead of having a nicely varying function response without any kinks or creases or anything, we might have a non-smooth response. If we have a kink or a crease somewhere in the response in the function surface, then that means at those points or those locations where we have a kink or a crease, then that function is not differentiable. And if it's not differentiable, then that has a big impact on the solution methods that are possible to use in solving that problem. Another class of problems that's important and interesting include function-valued optimization variables. So for example, what we've looked at so far includes vector-valued optimization variables. So we have a finite number of elements in the vector x. But what if we have something that where the input to the objective function is a function itself? So for example, a trajectory through time or something. And that produces, or that relates to a completely different class of optimization problems. This relates to an area called optimal control. That's a really interesting aspect of mathematical optimization that's important for other areas of engineering design. Here we're going to use nonlinear programming as a strategic choice to first learn about design optimization of physical engineering systems. Often the metrics that we use in describing the behavior of physical engineering systems are nonlinear functions. So we need an optimization problem and corresponding solvers that are capable of dealing with these nonlinear functions. Another type of optimization is referred to as linear programming, or an LP. And linear programming is really important for many other different types of optimization, but it's usually not sufficient for design optimization of physical engineering systems. And that's because, in general, the behavior or functions that approximate the behavior of physical engineering systems tend to be nonlinear. There may be linear elements, but there's usually at least one aspect that is important that is nonlinear, and so we usually end up using nonlinear programming. Also, failure modes for physical systems, so things like temperature constraints or stress constraints or volume constraints, these things can be modeled very well as inequality constraints. So we want to learn about optimization problem formulations that allow us to include these inequality constraints, or G of X in the notation used here. So limiting ourselves to just nonlinear programming formulations, things that typically can be described using this standard mathematical formulation. These allow us to formulate and solve a really rich set of important engineering design problems. So this is a great place to start as you're starting to learn how to formulate and solve engineering design optimization problems. But after you have this foundation, you can go on to learn a much broader set of engineering design optimization methods. And so you can do this either by taking additional follow-on courses, or if there are other research or other activities that you can get engaged in to learn some of these other techniques. What is engineering design? So we've talked about engineering, we've talked about design, we've talked about mathematical optimization. Now let's bring engineering and design together and answer this question: what is engineering design? What demarcates or what distinguishes engineering design from other types of design? Engineering design is not the only type of design. We have graphic design or fine art. That's definitely a creative design activity. Clothing or fashion design, food design, pastry design, architecture. This often is coupled with engineering design in that we need to have, say, structural stability along with the aesthetics of the architecture. Or garage tinkerers or makers. I definitely started out as a garage tinkerer and maker, and I continue to do this type of design, but that is different from what we might refer to as engineering design. We're going to learn in a little bit more depth what that distinction is. And one aspect of this is that successful design of engineering components and systems requires some sort of training in technical engineering topics. It's not something that a typical garage tinkerer can do. For example, would you build a suspension bridge that supports people either in cars or pedestrians just using intuition and trial and error to make decisions? This is a safety critical system. Or what about modern aircraft or electric passenger cars? These are really complex modern systems where these other techniques, the non-engineering design techniques, probably are going to fall short. We're not going to be successful in designing, fabricating, and actually getting it to work with one of these more complex and safety-critical systems. Design of systems that are complex relative to human cognition requires application of engineering analysis tools and systematic design strategies. So the kinds of things that we're learning in this class, you can think of as tools or extensions of human capabilities. When there are simpler things we're trying to design or things that are kind of on the human scale, then we can do a pretty good job designing using intuition or trial and error. But to extend what humans are capable of designing, that's where more sophisticated engineering analysis and design tools come into play. Engineering design methods. What is an engineering design method? How do I define that? It requires two things. One, a design problem formulation. And two, a way of solving that problem. There is a really wide range of possible design methods, and these can vary greatly in how rigorous they are or how formal they are. So on the informal side, for example, this may be appropriate for less complex design problems. Maybe we just have a mental model of the problem formulation. It's all in our head. We've not even written it down. So if I'm out tinkering in my garage, then this probably is a reasonable design strategy or a way of formulating the problem. And then as far as making design decisions, if it's something simple, then maybe I can just use my intuition, drawing upon my previous experience and trying to make good design decisions. Then we can think about more formal types of design methods, and these are needed for more sophisticated systems. We need to make a formal statement of often what we call system requirements. And we need a systematic organizational process. Maybe we use some kind of design rules, or maybe we're using design optimization as a strategy to help support making design decisions for something that's more complicated than is really reasonable just using human cognition. let's have a look at some different categories of design strategies. So not just design optimization, but some other general design strategies, and look at some of the pros and cons. And here I'm trying not to rank these strategies in any way. It depends on what your design goals are, which one is most appropriate to use for your situation. And I am going to talk in general, starting from the least formal toward the most formal strategy. But in some cases, maybe the least formal strategy is really the best way to go. And one way of describing this would be craft work, or making design decisions as you build, as you fabricate something. So, for example, during this working from home time period, I have discovered I really like using a standing desk. And instead of purchasing a standing desk, I found some scrap wood, and I used a really informal approach. I had a mental model for what I wanted to look like. I did take a few measurements, but it was not a very formal design strategy. And I just kind of made design decisions as I went. I did not have a complete description of the design when I started building. I made decisions as I went, and I made some mistakes. So it ended up being that to get my monitor arm to fit on the standing desk the way I needed to get it to fit, it was incompatible with the way I had designed things. And so my options were to either just start from scratch, throw it away, or try to make some modifications. So that's what the second strategy is what I did. I made some modifications, drilled some extra holes, made some extra cuts, got it to work. But here I'm not dealing with a really safety critical system. I'm not dealing with really demanding safety factors or anything. And so I had this wiggle room to use this design or make design decisions as I build sort of strategy. I use this trial and error approach. Things that fall under this category might be described as art or craftsmanship. This kind of activity is really helpful for building intuition. So even if you're an engineer who is designing incredibly sophisticated systems, it still is valuable to really have some hands-on experience and learn more about what I call the media that you are using to create. So sort of like, say, a sculptor or a painter. They need to understand how clay behaves, or how different types of paint behave, or how to mix colors. They need to understand their media and have intuition for their media. A successful design engineer also needs to have a really good understanding of the media that they are using to create, whether that's different types of materials, metals, polymers, and so on, or maybe electronic systems. An engineer needs to have a good, solid understanding of how the media they're using to create works. If we're using this sort of approach, this design as you build approach, the complexity of systems that can be designed in this way is very limited. Our human cognition only goes so far. We can only keep so many things in our head and manage them at the same time, unless we have some other kinds of tools to help extend human capability. The resulting performance and efficiency of the systems that might be generated in this way is limited, and there are a lot of other limitations that are associated with this kind of approach. One example is designed fixation. If we create a potential design solution in our mind, there's a chance that we might become attached to it. It might be hard to let it go, even if that's irrational. And especially if we are building something, if it's we're making something physical, there tends to be this emotional attachment to it. So, for example, when I was building my standing desk, I maybe was too attached to it. I did not want to start from scratch, and so I stuck with my original design, but I forced it to work. I made modifications to it. I guess it depends on your design goals. I'm pretty happy with my standing desk. It works great for what I need. But if I had a more complicated sort of engineering system I was designing, I probably needed to use a more sophisticated technique. So one step up in sophistication might be described as rigorous experimentation, and this definitely falls within the realm of engineering design. We support design decisions using data or information that we get through systematic physical experiments. We want to base our design decisions on evidence, not just our intuition. This becomes increasingly important as the systems we are designing become more complex, and also as we start to venture into the realm of systems that are very different from human scale things, whether that's human scale in terms of size or human scale in terms of time. And so things that we don't have really good innate intuition for, this is where we really need to use a more rigorous approach based on objective data. So this is a more objective and efficient design exploration strategy. So those of you who are students at the U of I, there is a course available to you that is called IE Industrial Engineering 400. This is a design of experiments course. It's a statistics-based course that uses a technique called ANOVA, or analysis of variance. And the basic idea is to first recognize we have a limited number of experiments we can perform. Each experiment costs something. It costs some time, it costs some money, and we have a budget of experiments that we can perform, a limited number of experiments we can perform. But we'd like to get as much valuable information as we can from those experiments. So how do we decide how to perform these different experiments? What are the different treatments? That's one term that's often used. Or what are the different specific designs that we might want to test to determine what's the best design? So if you're interested in some of these statistical techniques for rigorous experimentation, you might consider either taking this course or learning on your own about design of experiments. Here's another category that's another step up in sophistication, but it requires additional investment. And something that's really been a boon to engineering is the rise of computer-based models or computer simulations that help us to fairly rapidly predict the behavior of a system and do it pretty accurately. So things like finite element analysis or computational fluid dynamics or computational heat transfer. And with these kinds of tools, these types of computer simulations, we can use those to predict the effect of design decisions. So if we want to compare two different designs, we don't necessarily need to go and prototype both of those physically. We can instead create a computer model of both of them and then run a virtual experiment on them to predict the effect of different design decisions. And there are a lot of benefits to this. It's often faster or less expensive than physical experiments, although there are exceptions. There are definitely cases where physical experiments are going to take less time than it will take to complete an accurate simulation. Another value is that going through the process of developing these models that predict the behavior of different design decisions, that's a great way of gaining intuition. So not just the trial and error, but especially if you are relying on a physics-based model and understanding the underlying equations, that can really help you to gain some intuition for the behavior of the system and the effect of design decisions on behavior. And that starts to get into design intuition and design thinking that we're going to talk quite a bit more about in this class. These kinds of tests are helpful to discover what physical mechanisms are influential with respect to design problem. So are there certain things we need to make sure that we include in the model? If we're dealing with a fluid system, do we need a model that's capable of modeling turbulence at some level of fidelity, for example? If we are using this model or simulation-based design, that often can allow us to increase the level of design flexibility we have, the amount of complexity we can manage in the design problem. And we're going to get a little bit more formal about what we mean by design flexibility or design complexity as we go on through these lectures. But one way of thinking about it is design problem with very low flexibility. That might be just something where maybe we're just tuning a handful of continuous parameters. We're just tweaking some of the geometry of a system or something else, just a kind of a minor change. Whereas a highly flexible design problem is more like a clean sheet design where we are considering many, many different design options, the sky's the limit kind of thing. And in that case, we have what we call just a really vast, expansive design space. And that's harder to navigate. So there are trade-offs. If we have more design flexibility, we could discover highly valuable designs, high-performance designs, but there's a cost involved in exploring and navigating this very expansive design space. And if we're doing it using model or simulation-based design, but we're using our expert intuition to adjust the designs, or even if we're using design of experiments to try different designs, it may still take a really long time, especially if we have a very vast, very high dimension design space. So this is where we bring in design optimization. Say if we have many different design variables that we're trying to tune, it would be really inefficient to take a brute force approach and just enumerate through many different combinations of design variables and test them all, whether it's with physical system design or physical system testing or virtual testing. We'd like to be able to explore the design space efficiently. We want to find the best design without having to test them all. In this class where we're focusing on continuous optimization, we're going to get to the heart of this capability. Even if there are an infinite number of points in a design space, an infinite number of designs, how can we, in some cases, even guarantee that, yes, we have the optimum, we have the very best design among all of these points, and yet we did not have to test all of them? Of course, we can't test all of them if it's infinite. If we are thinking about optimization, we're not just trying to meet requirements. We're trying to make something better. A very standard sort of approach in systems engineering is requirements-driven design. That's what this acronym stands for, RDD. So we, in design optimization, are trying to exploit some of the flexibility we have in a design problem to improve the value of the design. It's ideal if using design optimization, we can maybe even make some new things possible, new functionality that was not possible using conventional design approaches, so that we can create and understand unprecedented systems. Another aspect of design optimization is it helps us to automate parts of the design process. Something I like to emphasize when talking about design optimization is that it's not sort of like a complete automation of all design elements. It's not just a push-button approach that's going to replace all engineering designers. It's more of a complement. We automate parts of the design process. We automate parts that maybe are better suited to optimization algorithms versus human expertise. So in this class, SE 413, this is what we are focusing on: engineering design optimization. It is not something to really think about as the best design approach, but it's one of several design approaches, and in some cases it's going to be the best choice to use. But in other cases, maybe if large safety factors don't matter, for example, maybe we can use a less intensive design strategy. Just thinking back to craft work, though, this upper left corner, this type of design, while it is definitely design, it's typically not considered engineering design. Engineering design involves some sort of engineering analysis that goes beyond just kind of decide as you build strategies. These design as you build strategies, these can be performed without engineering training. Folks without having taken engineering classes can have fantastic intuition and expertise for how technical systems work, for how metal behaves, or other aspects of the systems that they're designing, and they can do great work using this approach, but they are limited in the complexity of systems that they can tackle using a design as you build strategy. Engineering design method selection. If you're an engineering designer, you need to decide what strategy are you going to use to complete your design task. How do you choose an appropriate design method for your needs? Different design problems have different characteristics, and there's not just a one-size-fits-all strategy. There are a lot of questions that you can answer along the way in making this decision, how to approach your design problem. 1, what resources are available? Is it just you? What kind of computing resources do you have? Or do you have a whole team of multidisciplinary engineers whose expertise you can draw from? Is the system safety critical? How important is it that we are highly confident in the behavior of the system? If it's safety critical, then we're going to want to invest very significant resources into making sure we get it right. Is it essential to success that we reduce safety factors as much as possible? There's some different engineering design domains where this can be very different. So we can have two different cases that are both safety critical, but the importance of getting a small safety factor is different. So for example, if we are designing a bridge or a building that involves a steel structure, then it's definitely safety critical. We want to make sure that we're very confident in the design solution. But it's okay if we end up having a fairly heavy structure. We definitely want to keep costs down, but it's not going to have as much impact on the competitiveness of what we are producing as an engineering designer as, say, an aircraft or spacecraft. So in aerospace design, it is very essential to keep weight or mass down just as small as possible, and that often translates to having very small safety factors. We need to have the safety factor as small as we can to get the mass as low as we can, to get the performance as high as we can, but we still need to have really high confidence that the system is going to be safe. So how do we do that? Well, we need to have more rigorous testing, more rigorous analysis, and more rigorous design strategies, but that requires more resources to be successful in doing that. So that just gives kind of a sense of the trade-offs involved in deciding between different engineering design methods. Another big consideration is, what's the market like? Is there a lot of demand? If we are able to produce a particular technical capability, and if that requires a big investment, is there a good chance we're going to get a payoff? If that's the case, then maybe it is worth the investment to use a sophisticated, intensive design strategy to produce a high-performance system if there's a good chance we're going to get a payoff for that down the road. So in what ways might more sophisticated engineering design methods be worthwhile to use or create? So we talked about some examples here, say in aerospace system design. It is helpful to have design methods that allow us to expand what is capable, to push the performance envelope while still maintaining high confidence in the safety of these systems. But that's just one example. I'd like to take a step back and think about the impact that effective engineering design can have on the world, that it can have on humanity. Here's a pretty well-known famous woodcut of Archimedes figuratively using a lever to move the world. He said if he had a lever long enough, he could move the world. And as designers, as engineering designers, we can have a big positive impact on the world. And as we create or learn more effective design methods, that's essentially creating a bigger lever. So as we move from garage tinkering to rigorous experimentation, we are extending the lever. We are enhancing our capabilities of impacting the world, and acquiring the capability of using design optimization in practical and effective ways is another way of creating a larger lever. There are a number of challenges in modern engineering design that are very important to be aware of. There are fundamental competing factors as we are approaching complex or design of complex engineering systems. So here's one example, just a conceptual plot showing how a systems engineering process might proceed through time. And so the horizontal axis represents time as we're moving forward in a systems engineering process. There are two elements to be looking at here. One is system knowledge, and one is design flexibility. Early in the design process, we have very little system knowledge. As we proceed through the design process, we gradually obtain more data, more evidence. We increase our system knowledge, our confidence in that knowledge. But then the other element here is design flexibility. At the beginning of the design process, we have lots of design flexibility. We have lots of options at our disposal. We're not as locked in. But as we start to proceed through this design process, we start to make decisions. And maybe we can reverse some of those decisions, but usually there's a cost involved with reversing those decisions. So there's a little bit of inertia or stickiness. And as we proceed through the design or systems engineering process, design flexibility typically goes down. These are competing elements. We ideally would like to have maximal design flexibility and maximal system knowledge at the same time. But in reality, that doesn't happen. So we would like to produce design tools or design methods that allow us to shift these curves around. Advances in engineering design methods help us to accelerate system knowledge acquisition, for example. So if originally maybe using a traditional engineering process, we're on this dotted line. If we apply a more sophisticated process, maybe we can accelerate the acquisition of knowledge with respect to design about the system we're trying to design. And then conversely, if we're looking at flexibility, we would like to prolong design flexibility. We'd like to have the ability to change our design decisions later in the process if we can. And if we're using a design automation approach, like a design optimization strategy, then that may reduce the cost of changing design decisions. If it's automated and we discover we need to update something, we need to adjust something, then it's a little bit easier to go back to an earlier phase, make the change, run the optimization problem again, and come up with the new design decisions. So that is a way of pushing design flexibility, this design flexibility curve, farther out into the future. I want to talk just briefly about engineering design methods research. There are many different flavors of engineering design methods research. The strategy that in my research group we use, I like to describe as design method creation and analysis. We work on creating new methods, but that's not all of it. We work on analyzing those methods so that we can understand them in a way that's useful for practicing engineers. So we create new formal engineering design methods that address unmet needs. Maybe there's not an existing method that can solve an existing design problem in an effective way. And these kinds of new methods can help us make it possible to create new technology. Maybe it helps us to reduce cost further or reduce the time it takes to design a particular type of system. So, for example, what if we create a new design optimization strategy that makes it possible to automate the design of a system that previously was not compatible with optimization? Maybe there was just something about the nature of that design problem that made it just impossible using current practice for design engineers to apply optimization. But we do some research, we make some discoveries, and we create a new way that makes it possible to optimize that system. So that's a way of providing value. Or another way of providing value through creating new methods could be, suppose we already have a system that we know how to apply design optimization to. But what if we want to improve the fidelity with which we solve that optimization problem while simultaneously reducing the overall implementation and solution expense? And so that's going to help us make better design decisions and make those better design decisions faster. So that's about method creation. That's not all there is to the research. We also have method analysis. So we take either existing methods, existing design methods, or the new design methods that we've created, and we analyze those to produce new design knowledge based on evidence. This kind of knowledge is important for helping practicing engineers decide what design method might be best for their current design activity. So we try to answer questions along the lines of, if your design scenario has properties X, then use method Y. So that kind of thing is helpful for practicing engineers. And this class, it covers existing knowledge that is foundational to the successful application of engineering design optimization. Okay, now that we've gone through the definitions of engineering design, optimization, and engineering design, let's talk about all of them all together: engineering design optimization. Here, using an engineering design optimization approach, we have an engineering design problem that we've formulated or modeled as a mathematical optimization problem. There is a difference between the real engineering design problem that the human engineer or engineering team needs to solve versus the mathematical optimization problem. The mathematical problem is really just a model of the decisions that we need to make as design engineers. Once we have that formulation, then we can solve that optimization problem using solution methods for mathematical optimization. So some kind of numerical optimization solver, an optimization algorithm, and we're going to learn about a subset of those in this class. If we solve that problem successfully, then the result is a design that is optimal with respect to not the original engineering design problem, but the nonlinear programming problem formulation. So if we solve the problem successfully, and there are ways of verifying when an optimization algorithm terminates that, yes, we have in fact found an optimum, we can say confidently that, yes, this is the optimal design with respect to the nonlinear programming problem that we defined. But then the big question is, how accurately does the nonlinear programming formulation reflect or represent the original underlying engineering design problem? So if we have a high fidelity formulation or a formulation that's really accurate, then the resulting optimal design from the optimization algorithm, then that could be a really good thing to base our design decisions, our actual design decisions on. The formulation and solution process, this process of formulating an optimization problem, solving the optimization problem, is usually very iterative. We gain knowledge through this process, and sometimes that knowledge helps us to go back and adjust the design optimization formulation so that it does a better job reflecting the original design goals or being a better model of the actual engineering design problem. This course is focused on helping you learn to execute this iterative process successfully, specifically for the unique challenges of physical system design, as we've discussed briefly before. And this motivates nonlinear programming formulations, or more specifically, the unique challenges of physical system design motivates the use of nonlinear programming, or using optimization formulations that allow for nonlinear objective and constraint functions, as well as inequality constraints. So here I talk about a process, an iterative process. What does this look like exactly? Let's talk about what might be called the engineering design optimization problem formulation cycle. The first step is to generate a problem formulation. And there are many elements involved with this, and we're going to dig very deeply into problem formulation, how to go about doing it. And in addition to just generating the nonlinear programming formulation, we also usually will do some type of initial formulation analysis. There's some checks that we can do to see if this is a good formulation and catch potential problems before we invest additional effort into solving the problem. If we catch some of these potential issues, we might have to iterate at this stage, iterate on the formulation before we even try to solve it. Once we have a formulation we'd like to test, then we go and apply a solution method to solving this problem. We are going to learn about analytical solutions for optimization problems. These typically only apply for fairly simple optimization problems. So for most practical engineering design optimization problems, we need to use a numerical solution algorithm for optimization. Now that we have solved this problem, that's not the end. That's not the last step. We need to have the knowledge, the expertise to understand what that problem means. We need to analyze the optimization solution. We need to learn how to interpret the resulting design, and there's some other quantitative aspects of the optimization solution that can provide a lot of insight. It can tell us something about how confident we can be in the solution, or other aspects of how the problem formulation might be improved. And if there's some indication that there is improvement available and that it's worth the effort, then we can go back to the formulation stage, adjust the formulation based on the new knowledge we have, and then go back through the solution and analysis process. So in this class, you're going to be going through this, especially in the semester project. I anticipate that most of you will go through at least 2 cycles of this process. I need to see more in your projects than just a single pass through this process. I need to see that you've really acquired the ability to analyze formulations and not just solve the problem, but really dig into the results of the solution and determine how you might go back and improve the formulation to help this become a better model for the actual engineering design problem. If we're just talking about specifically the formulation step, one way I like to think about this step is starting with our original engineering design problem. Sometimes this might be called a framed engineering design problem. This is a fairly early stage in a design process where we're describing the overall scope of the problem, or what are the elements that are within the domain of the design engineer to be making decisions about? What are the assumptions that we're going to be making in this problem? What are the overall design goals? Once we have written this down, we've defined what the underlying engineering design problem is, then the next step, based on knowledge gained in this class, is to construct a mathematical optimization problem formulation. We want a formulation that is well posed. We're going to learn more precisely what we mean by a well posed problem. We need a problem that's solvable. And we also would like a formulation that models or approximates the original target or original engineering design problem well. Here we're looking at just the problem formulation step. And after we formulate, then we solve, we analyze, and then we may go back and iterate. The process of effective problem formulation requires not just knowledge of optimization theory and algorithms, numerical methods, but it also requires expertise in other areas, including design thinking and knowledge about the engineering application domain. If we are designing an aircraft, we better know something about how aircraft systems work and how to model the important aspects of aircraft. We're going to learn more about design thinking and how this way of thinking is different from what you tend to get trained in most engineering analysis-oriented classes. When we come up with an initial formulation, it's important to remember that we need to perform some initial analysis on that formulation before going direct to the solution, and so we might have some iteration required at the formulation stage. This course covers systematic strategies for engineering design optimization problem formulation and analysis. One effort I'm trying to make is to make it possible within a single course to get some serious expertise in this process. How do you go about this in a systematic way that improves your chances of success? When I learned design optimization, I went into a lot of depth with the mathematics of optimization, and I worked on lots of different projects. And looking back, I learned this process really by trial and error, or talking to others and learning from others who are working with this process. So I hope that in this class, by focusing on this systematic approach to formulation, solution, analysis, and this iterative improvement cycle, that I can help to accelerate your ability to use engineering design optimization in an effective way on practical engineering design problems. I keep talking about engineering design optimization formulations. Well, what are the elements of the formulation? We've looked at the standard form for a nonlinear program, but what are the main decisions that we need to make about a design optimization problem formulation? One is a formal design representation. How are we going to specify the different design candidates that we're going to consider in this problem? Another way of thinking about this is design variable specification. So for example, are we just going to be tuning a few geometric parameters? Or are we going to be attempting a more ambitious clean sheet design where we have tremendous design flexibility? This is a big decision. If we're just tuning a few parameters, then that's a much easier problem to solve typically. But if we are allowing profound design flexibility, that can be a very significant undertaking. Comparison metrics definition. If we have more than one design candidate, and if we have any kind of design degrees of freedom, then this is the case. We need a way of saying whether one design is better than the other if we're going to do any kind of optimization. We need an objective way of ranking design candidates. And to do that, we need to use what I call here comparison metrics. And then once we define these comparison metrics, and these in design optimization with nonlinear programming correspond to objective functions and constraint functions, we need to address this question. How well does this ranking that we're using with the optimization, how well does that ranking align with the real design preferences? So this might seem a little bit abstract at first, but basically we need a way of ranking different designs, but we have to do it in a way that can be automated. We have to do it in a way that will be compatible with working with an automated optimization algorithm. In most cases, we can't just check the human preferences to see which one is better if we're using an optimization study. But it's really the human preferences that we are after. So how well does this automated ranking strategy that we're using with optimization, how does that align with the real design preferences? So there are different levels of accuracy that we can attain in this dimension of defining comparison metrics. So finally, the third aspect of problem formulation is predictive modeling. Given a design X, so here in this class we're thinking about this vector X as the design definition. It's a specific set of values of these design variables. So given a design X, how can we, in an automated way, evaluate comparison metrics, such as an objective function or constraint functions? So this is where we bring in models of an engineering system. Maybe these are simple models that maybe you've learned in some of your foundational engineering classes. Say if you are in mechanical, aerospace, or systems engineering, maybe you've taken courses in statics and solid mechanics, and you know what beam equations are, or other types of models for structural or mechanical systems. Those are the kinds of things we're talking about here, the predictive modeling. And we need a way of mapping a design that is defined using our formal design representation, in this case, the design vector X, and mapping that to the comparison metrics. Or in other words, given a design X, what is the value of the objective function? And if it's a constrained problem, what are the values of the constraint functions? And these predictive models must be compatible with the optimization algorithms. And a really important point to make here is that the effort required to construct predictive models that are effective for use with design optimization can be a really significant effort. This is often one of the biggest bottlenecks. There is a difference between an engineering model that is used for design optimization versus a model that might be constructed for other purposes. We're going to go through a topic in this class where we address this specifically. How do we develop models that are appropriate for design optimization? And often, say even if a system has an existing model that was developed for some other purpose, it often is not complete, at least from the perspective of design optimization. And so it needs some development effort. So in practice, this is something that really needs to be accounted for as far as how much investment is required in implementing a design optimization strategy. And then in this class, for your projects especially, you need to be very cognizant of the effort that may be required for constructing your models. And in this class, you have the option of doing either a standard project or an intensive project. It's the intensive projects that's primarily for graduate students who likely have some sort of experience with predictive modeling for some engineering domain they have some experience in. And these intensive projects are intended to take more time and require some additional investment in the predictive modeling and other aspects of the problem formulation cycle. But then with the standard projects that the majority of the class will be working on, you want to keep the predictive modeling aspect of your problem just as simple as possible. So using things like beam equations, for example, that's appropriate for a standard project as opposed to, say, linking structural design with finite element analysis. So you have to be really careful with how much or how ambitious you get with the predictive modeling aspect. I really hope that all the groups in this class can have a really rich experience in going through this cycle of problem formulation, solution, analysis, and improvement. But if you are too ambitious with your predictive modeling, you run the risk of going the whole semester barely getting your model done and not having time to go through the iteration. Here's a thought experiment just to explore how we might go about formulating an engineering design optimization problem. Say here we have this front suspension system of a car. Here we have this subframe. We have the sway bar. Here we have struts, so the helical compression springs and dampers. And here we have an upper control arm, lower control arm, steering knuckle, or the uprights. And here it's a front wheel drive car. It might also have rear wheel drive, I don't know, but here are the half shafts, the drive shafts that come from the transaxle here in the front of the car. And we also have the steering system up here, the steering rack, and this is what exerts a force to the steering knuckles that then turn the wheels. Anyway, so we have all these components in this front suspension system, and it has a lot of different functions. It needs to support the sprung mass, the weight of the car as it's resting on the road or driving over the road. So it needs to provide a force, a connection, a mechanical connection between the main part of the car and the road, but it needs to provide some kind of vibration isolation. So there's a comfort aspect to this. There's a comfort functionality, but then there's also handling. We need to maintain good grip between the tires and the road. We don't want to have too much fluctuation in the force at the tire contact patch, and that'll help us have better handling. And there are lots of really interesting, complex geometric or kinematic aspects of the suspension that will affect handling and lots of other things. And then, of course, we also have the steering system. So we have all of these things that are different functions or different ways of comparing different suspension designs. And let's think about how we might answer these three questions. How can we describe design alternatives? What are some simple ways of parameterizing this design? Maybe we're only doing a few simple things like adjusting the stiffness of the springs or the damper. Maybe we're just looking at a few simple elements of geometry, such as the dimensions of these linkages, and that'll change the kinematic behavior or the way these components move through space, and that'll have an impact on the functionality of the system. So we have those possible design decisions, but what if we took a step back and tried to take a more free-form design? What if we were actually including things like not just the length of the control arm, but maybe also the detailed design of it, the shape of it, or maybe even the layout of the system, the configuration. This is a 4-bar or a short long arm suspension system. There are other configurations available. We could use a McPherson strut suspension. That's less expensive, but that usually doesn't perform as well. So those are examples of design decisions and different levels of fidelity or different levels of flexibility that we can have in describing design alternatives. So that's one part of the formulation. Next, how do we quantitatively compare design alternatives? Say we have 3 or 4 different suspension designs based on the design representation. that we have defined, we need some way of ranking them. We need a way of saying whether one is better than another. And this is where things get a little bit tricky. So there's not just one functionality here, but we have multiple things to be thinking about. It really depends on the purpose of this vehicle. Is this something where comfort is the highest priority, or is handling the highest priority? So we need some way of ranking these design alternatives, even though the behavior of the system really is pretty complicated. After we define this strategy for ranking, we need a way of mapping the definition of the designs to the comparison metrics. How do we predict performance? What kind of predictive model are we going to use? Are we going to use some really simple equations that are maybe based on significant simplifications? Or at the other end of the spectrum, are we going to use a complex nonlinear multi-body dynamics simulation like Adam's car, a software tool that's really expensive but really good at predicting handling behavior? Or maybe actually going out on a test track and using physical prototypes and testing the actual behavior of the physical car. So those are different levels of fidelity that we can use in predicting performance. Comparison metrics. To rank different design candidates in terms of decision maker preferences, so whether that's the customer who's purchasing, say if we're using the car as an example, or whoever's making the final decision about what is to be made. To rank different design candidates, if we're thinking in terms of decision theory or decision science, often we talk about a utility function. An accurate utility function is one that matches with the preferences of the decision maker. Actually constructing a utility function that accurately represents preferences can be really difficult. Sure, we can take surveys of human preferences, but preferences can change over time. And it's often a very challenging thing to get a really accurate utility function. In engineering design optimization, we've got to start somewhere. We've got to make some progress. So we have to make some assumptions here. And it may not be possible to have a perfect utility function. But here we're going to assume that it's possible to rank our designs using this formulation where we have constraints and an objective function. So the objective function, that's going to be different, or it's a model, it's an approximation of the true utility function. Here, we want to be able to rank candidates, and we need design candidates that satisfy these constraints. If it satisfies these constraints, we say that it's a feasible design. If it's not a feasible design, we throw away all of those infeasible designs. But then among the feasible designs, we need a way of comparing them. And so we evaluate the objective function value for the feasible designs, and we want to find the design that has the smallest objective function value. We want to either minimize or maximize that. As I mentioned before, in standard algorithm implementation, we typically assume that it is a minimization problem, and it's pretty easy to convert from a maximization problem to a minimization problem. Constraints, these are requirements that must be satisfied. And this particular model with the nonlinear objective and constraint functions, and especially the presence of inequality constraints, is really useful when designing physical engineering systems. So let's go through a little example or a little bit more detail to describe what do I mean? Why is this useful for physical engineering systems? So let's have a look at inequality constraints specifically. Often, failure modes for physical systems involve some kind of threshold value or limit. So like a temperature limit, a voltage limit, a stress or strain, deflection limit. And we want to make sure we satisfy this limit. It's necessary to stay on one side or the other of this limit. But in a lot of these cases, there's no real value by moving farther away from this limit. So for the example, say in a structural design stress, if we meet our stress constraint, we've not exceeded whatever the allowable stress is, then we have a feasible design with respect to stress. But we could reduce the stress. We could beef up the system. We could make the components thicker and reduce the stress. Well, what's the effect of that? Well, so that reduces the stress, but it's going to increase the mass of the system. It's probably going to increase the cost of the system. But did it help anything? It really depends on what the objective function is. But if increasing the mass did not help the objective function, then there's really no value to reducing the stress a fair amount below the stress limit. And so it's really helpful when we have this sort of threshold behavior in physical engineering design problems to have the ability to model this using inequality constraints. So these failure modes with threshold limits are well modeled as inequality constraints. And when constraints appear in design optimization problems, they usually are inequality constraints. There are some exceptions, and there are some more advanced problem formulations that use equality constraints in some creative ways. But for the most part, we're going to be dealing with inequality constraints in the practical engineering design problems we're talking about in this class. So for example, going back to this stress example, say we are using an extremely simple model for the stress in an axial component, structural component that's in tension. And that's just going to be the axial force divided by the cross-sectional area. And we want to make sure that this axial stress is less than or equal to some allowable stress value. And maybe that already includes a safety factor wrapped up into it. We can then convert this into a form that is compatible with standard optimization algorithms. This is called negative null form. We'll talk more about this in the future, but here we are essentially defining a function here, g, and suppose a is the design variable, the cross-sectional area of this tension member. Here, g of a is the inequality constraint function, and that is equal to the actual stress minus the allowable stress. And the standard way of defining these inequality constraints is such that if the function value is less than or equal to 0, then we say the design is feasible. And then if we look back up here, if g of a is less than or equal to 0, then that's going to be equivalent to the stress f over a being less than or equal to the allowable stress. So this is just a transformation that is good to get familiar with, and that shows up here in the problem formulation, g of x being less than or equal to 0. This is a standard way of formulating these constraint functions. Let's go back to concepts regarding the engineering design optimization problem formulation cycle. It's not a push-button tool or a black box that we can use to replace design engineers, or design engineers can simply just apply once to a realistic problem and be done. We need to go through an iterative process between formulation definition, formulation analysis, solution, and interpretation and analysis of results. This requires skill and expert intuition in several areas. And in this class, I'm hoping to help you to develop the skill and knowledge required to go through this cycle. It, of course, requires knowledge of the math behind optimization and whatever's needed for modeling your system, the predictive modeling for your application. It requires knowledge of numerical methods. In some cases, maybe there are nice closed form solutions like simple beam formulas for predicting stress or deflection, but often we don't have closed form solutions. And if we're talking about solutions to optimization problems, we need to use numerical approximation methods to approximately solve the optimization problem. For very simple optimization problems, there can be closed form analytical solutions, but for practical problems, we usually need to use a numerical optimization algorithm. This requires engineering application domain knowledge. You need to know something about the domain you're trying to optimize. And this is often a good opportunity for collaboration between someone, say, who really knows optimization and understands this problem formulation cycle and is working with someone who is an expert in whatever the engineering application domain is. You also need to know very well this engineering design optimization problem formulation cycle. What are the details behind each of these different tasks, and how do you transition from one task to the next? And of course, a theme running through all of this is design thinking skills, learning how to think as a designer and not just doing engineering analysis. Okay, one last main topic, just thinking about engineering design optimization as a decision support tool. Engineering design is a decision-making process. So just as an example, try to think about some examples of engineering design decisions that a practicing engineer might be making. Decisions like, well, what material should I use for a component? What should the geometry be for a particular component? When we formulate an engineering design optimization problem, that is a model or an approximation of the underlying engineering design problem. And this model can be useful for helping us to make the actual decision. So there's a difference between the result of the optimization problem and the decisions that the design engineer needs to make. If the model is really accurate, the design optimization formulation is a really accurate model of the underlying engineering design problem, then maybe we could use the result directly in the actual design. But often there's some type of interpretation or judgment that's required before making the final design decisions. The problem accuracy with respect to the original design goals can vary. So just going along with what I just described about the accuracy of this formulation from the perspective of the original design problem, that can be either very accurate or less accurate. And let's talk about different levels of problem formulation fidelity. If I say a problem, an engineering design optimization problem formulation is high fidelity, then that means it does a really good job modeling or describing the actual engineering design problem. The resulting optimal solution of a high fidelity formulation is going to be an accurate approximation of what might be the actual optimal design in reality. The resulting optimal design variable values in this case could be used directly in final design decisions, but the trade-off here is that actually implementing and solving high fidelity formulations, this is going to require really significant investment, often very high investment in model development, and it can require very high investment as far as computational resources as well. And this level of investment, it might not always be worthwhile or possible. So as someone who's really interested in design optimization, I feel like I definitely have a bias toward trying to formulate and solve the most comprehensive, the most accurate, the most crazy design optimization problem possible, but we have limited resources, and it might not be worth the investment of our resources into solving a crazy hard optimization problem. Sometimes we need to back off from that and think about what is an appropriate level of investment into our design optimization efforts. So let's look at the other end of the extreme, low fidelity engineering design optimization formulations. In this case, the optimal solution does not necessarily accurately reflect what the actual optimal design is. So in other words, if we got our design vector X out of this optimization problem, the optimal vector X, and then we tried to actually build the design based on that vector X, we might find out, oh, well, because our models were so oversimplified, this actual design is not even feasible. It's not even going to work. And so we may not actually be able to use the values in the design vector directly in the final design decisions. These resulting values really are just notional, and they shouldn't be used directly. So there's less investment involved. It takes less effort to formulate and solve a low fidelity problem. But if we can't use the design variables directly, the resulting optimal design variables, why go through this effort? Why is it worth any investment? There are other valuable outcomes we can obtain from engineering design optimization besides just getting the optimal design. So for example, if we look at the resulting optimal design and compare it to a baseline design, it can give us some really good insights into what direction we should be moving with our design decisions. Or it could reveal some interesting physical mechanisms or strategies that are possibly really helpful for the actual design. We can do things like parametric studies. We can do some trade-off studies and look at trends. And this can generate insights that could be very useful for the actual design decision. So even if we don't generate an optimal design that can be used directly, it can still be very worthwhile going through these sorts of studies. These insights can inform engineers making the actual design decisions. With this context, it makes sense perhaps to ask this question: when does engineering design optimization make sense to use? One just hard requirement for using design optimization is we must have predictive models that are appropriate for design optimization. Either they have to exist or we have to create them, and they have to be sufficiently accurate for predicting the effect of design changes on comparison metrics. We have to have one or more design degrees of freedom. If we have a large number of design requirements in a problem and not that many design decisions, there's a chance that these requirements are going to overly constrain the problem, and we may not have that much design freedom. We might not have that many feasible designs to compare, and then if that's the case, then that might not be worth going through an optimization study. If the potential for improvement is very probable and the potential improvement is significant, then it may be very worth investing in design optimization studies. Something I'm really interested in typically are cases where there's the possibility of non-obvious solutions. So if we have a design problem and maybe we have some background in the physics behind it and the application behind it, maybe if it's a fairly straightforward problem, we can just use intuition, or it's just obvious what the best answer is. And we'll go through some examples of obvious versus non-obvious solutions down the road. But what about cases where just looking at the problem, thinking about the problem, we can't quite tell just through intuition what's going to be the best design decision? There may be some complicated trade-offs involved or complicated physical phenomena, some things that we just can't completely wrap our mind around. And in that case, that's what I would call a non-trivial engineering design optimization problem that could result in some non-obvious solutions. So if going through the design optimization effort generates some designs that we could not have arrived at using other methods, then that could be very valuable. Another requirement is that our problem formulation has to be solvable. There has to be some kind of solution method, optimization algorithms that are compatible with the formulation of interest. And in this class, we're pretty much going to stick to problems that have real continuous variables and continuous smooth objective and constraint functions. So we're just looking at one class of optimization problems. This point is a very important thing to look at when you start to expand the class of optimization problems you're considering, if you're starting to include some kind of non-smooth functions or discrete variables, for example. There are a lot of other factors that exist in making this decision. When does design optimization make sense? And usually we can't say definitively at the beginning of a design optimization effort, really, if there's going to be a net benefit. There is some risk involved in deciding whether to use design optimization or conventional engineering design methods. And to have a definitive answer to this, well, really, we'd have to have evidence. We'd have to really solve the problem both using a conventional design method and with design optimization. And then we've solved it twice, and if we are in engineering practice, well, that's not a very efficient way of going about solving your design problems. By gaining the knowledge and some of the intuition required to help support this decision, whether or not design optimization is worthwhile, and what level of design optimization fidelity is appropriate, that sort of knowledge is a core course objective. Let's make some observations in summary about engineering design optimization. Here, we are very interested in translating a real engineering design problem into a solvable mathematical optimization formulation. This requires application of optimization theory and the algorithms, the numerical methods. It involves the development of system models that are compatible with optimization. It requires application domain knowledge. So, for example, an understanding of the physics behind the systems, practical considerations, often historical design knowledge is useful. This is usually an iterative process. It's not a push-button magic solution approach to engineering design, but it can be used in many different ways as a decision support tool. Analysis of results from engineering design optimization is very important. It's possible to extract valuable insights that go beyond delivering an optimal design, and this analysis of results can help us to go back and refine the problem formulation to get even better results. This can be very helpful for practical engineering design under certain conditions. Let's talk briefly about what are the topics coming up ahead in this class. So in this video, we did a big, broad overview of engineering design optimization as a topic and kind of define the scope of what we're going to cover. And here I'm going to list very briefly the topics that are coming up in sequence. And here with this class, there are relatively few prerequisites, basically math and some background in engineering and an assumption that you have some programming experience. So the first topic we're going to go through is algorithmic thinking and some programming basics based in MATLAB. This is basically to get everyone up to speed, make sure everyone's on the same page. And we're going to have a lot of programming tasks through this course as we learn more and more elements of optimization algorithms and also using those in actual design optimization practice. We're going to get some hands-on experience using some of the core MATLAB optimization functions. That's in your second homework set. We're going to go through some of the mathematical preliminaries. There are a lot of things that are going to be reviewed that you've seen before, but there are going to be some new things. Most people probably, for example, have not gone into depth with what are convex sets or convex functions or matrix-based calculus. These are things we're going to cover in a fairly succinct way and make sure that everyone has sufficient foundation to move forward with the optimization theory and algorithms and go through that in a very effective way. I'm not assuming that you've had any course in numerical methods previously, other than most students in going through Calculus 2 have gone through some basic numerical methods. And with that as the only assumption, I am going to provide some foundations for numerical methods, things like, how do we deal with round off or truncation error, dealing with discrete computers or discrete math, floating point representations, that sort of thing. There are a lot of things that you need to be aware of as we move forward using numerical methods that are approximate solvers for these optimization problems. We're going to go really deep into design optimization problem formulation and the formulation cycle. We're going to go through a number of examples. And then after all of that, we're going to have our first exam. Before we get into really any of the deeper mathematical theory, then we're going to have this section on unconstrained optimization. We're going to start off with the mathematical fundamentals. We're going to derive and implement a number of different optimization algorithms, see how to apply those, and also perform solution analysis. And that's an important part of the problem formulation cycle. Then we're going to move on to constrained optimization, which is what we're really interested in for engineering design. Constrained optimization, it builds on what we learn in unconstrained optimization. But as we mentioned, with physical system design, with failure modes, typically those involve inequality constraints. And so to really solve engineering design optimization problems, we need to account for constraints, and we're going to learn how to do that. We're going to go through and see how the mathematics of optimization with constraints is different. We're going to, again, derive some algorithms, see how to implement those, and perform solution analysis. And then now that we have this ability to solve constrained optimization problems, then we can start going through the complete problem formulation cycle. Through all of this, you have a semester project that's an opportunity to pull everything together and gain skill in the overall engineering design optimization process. That's the scope of this course. I'm going to very briefly touch on a few topics you might be interested in that build on this course and go beyond the scope of this course, and then that'll be the end of this lecture. Related topics beyond SE 413. There are a lot of different optimization algorithms that you can explore and learn about. It's great to know about the different solvers that are available, what their strengths and weaknesses are. There are certain conditions where some algorithms will perform better. We're just going to learn a few basic algorithms in this class. It's not going to be a comprehensive review, but after this class, you'll be in a great place, a great position to go on and learn about many other optimization algorithms. We're going to be focusing in this class on what are called gradient-based optimization algorithms. So in Calculus 3, you've learned about gradients. These are essentially derivatives for multivariate functions, and the optimization algorithms we're going to learn about primarily in this class rely on gradient calculations, and that can really speed things up. You can also learn after this class more about gradient-free methods. So things like evolutionary algorithms or genetic algorithms, particle swarm optimization, pattern search algorithms, direct or directed rectangles. It's a global optimization method. And hybrid optimization methods. These are super useful for practical optimization that help us to improve the chances of us finding a global optimum. And in practical engineering design problems, we usually cannot ever guarantee we find a global optimum. So combining something like a global search algorithm, like a genetic algorithm, with a gradient-based method that can very quickly get to a precise solution, that's one type of hybrid optimization method. And those are often very useful in practice. Generative design is another really interesting topic that can be used as an abstract design representation. We've done a fair amount of work on generative design in my research group. So you can think of this as another aspect of problem formulation that helps to solve classes of problems so we might not be able to solve otherwise. And there are some generative algorithms that have now found their way into commercial software, and that's very exciting to see some of these developments. You could go into deeper treatment of optimization mathematics, and this is largely available through graduate level courses. There are a number of courses at the U of I that go deeper into nonlinear programming, the mathematics of nonlinear programming, or convex optimization, this more specific subset of nonlinear programming, or courses that focus on linear programming. Another very exciting topic is optimal control, and this is essentially the process of finding time-varying trajectories for control inputs that are optimal. So if you have a background in controls, this might make a little bit of sense to you, but if you've not done anything with control systems, don't worry about that. But it's a really interesting topic area. Another area of very active research is multidisciplinary design optimization. This is basically the case where we have two or more different physics disciplines, so things like aerodynamics and structures, or more, things like thermal analysis or electromagnetics, all combined into the same system, and these different physics domains are interacting with each other. Maybe we have different subsystems interacting with each other. We have all these interactions. That becomes a really hard design problem to solve. And there's a whole class of more advanced design optimization methods known as MDO that help us to deal with the specific challenges of these difficult multidisciplinary optimization problems. Also related to that is simulation-based design optimization. I'm developing a course that's going to be combining MDO and simulation-based design optimization that will build on SE 413. It might not be available for at least a year or so, but these are other topics that can help to build your ability to solve practical engineering design optimization problems. Another topic that's important to my research group is called control co-design optimization. This is basically a specific type of MDO where at least one of the disciplines is control system design. And there's a lot of what we call design coupling between physical system design decisions and control system design decisions. And there's actually a lot of activity in this area right now. There are several government-funded research programs right now, some from the Department of Energy, for example, that are supporting the investigation of using control co-design optimization methods to improve engineering performance in a number of different domains, including carbon capture and sequestration, or various different types of renewable energy. So, for example, floating offshore wind or hydro turbines, either ocean current turbines or river current turbines. Another big area is topology optimization. There are courses at the U of I that you can take here, and there are some really fantastic, efficient optimization techniques that can solve some really high-dimension, complicated material distribution optimization problems. Basically, if, say, we're designing a structure or a thermal system, where should we put the material to be most effective for whatever the objective is. System architecture design is another big area, and that is a type of discrete optimization that involves algorithms for searching through a space of different graphs. So there are a lot of exciting areas that you could go on to beyond what we cover in SE 413, so you can consider this to be a foundation for many different exciting topics. All right, that's the end of this video. I hope it was helpful, and I look forward to future lectures. Thank you.